This video is about input offset and input bias. It corresponds to sections 18.2.4 and 18.2.5 of the Applied Analog Electronics textbook. Now, when we're talking about input bias, input offset, we're talking usually about the properties of a differential amplifier. Let's say an instrumentation amplifier, for example. So, differential amplifier has a positive and a negative input. Let's call those VP and VM. It's got some sort of gain, and it's got an output V out, often with a specific reference voltage Vref. And the ideal behavior of this is that V out minus Vref is the gain times VP minus VM. So that when the two inputs are equal to each other, the difference between them is 0, the output is at Vref. So this would be great if we could always get it, but we can't always get it exactly. We've got real-world parts, things may be a little bit off. And one way that they can be off is that you might not get exactly at Vref when the input's 0. You may have to adjust the input a little bit away from 0 in order to get V out to be equal to Vref. And that adjustment that's needed to the input, so what is VP minus VM when V out is equal to Vref? That is called the input offset voltage. And it's a very important parameter of our amplifiers because we often have to worry about, all right, how much gain can we put on this amplifier? Well, if the inputs have a large offset, then we can't amplify very small signals a lot because we'll be amplifying this input offset as well. And that means that we have to worry about maximum gain we can get based on the range of how far can V out get from Vref, which is often based on things like the power supply and other properties of the amplifier. So the output range is limited, and that means that the input range is limited, but the input offset voltage contributes to part of that input that has to be amplified. Okay, so how bad is it? Well, that depends on how much you're willing to pay. Generally, instrumentation amplifiers do a better job of this than op amps. So for instrumentation amplifiers, you'll generally see that this output voltage, I'll just call it V offset, is going to be less than about 250 microvolts. About 90% of the instrumentation amplifiers that DigiKey has in their catalog have an offset specification of less than 250 microvolts. Obviously, if you're willing to pay a lot more, you can get a smaller input offset. And for some specialized applications, you may have to put up with a larger one. For op amps, they're usually not as good. Maybe about 3 millivolts. And again, that 3 millivolts is what about 90% of the op amps in the DigiKey catalog have as their offset voltage. These things obviously are not always perfect specs. The specs are usually done at 25 degrees C, and quite often as you raise the temperature, the specs get worse. So you have to read your data sheet very carefully if you're going to be using something outside of just the perfect testing conditions. But notice that instrumentation amplifiers much tighter than op amps. It's one of the things you're paying for when you spend a lot more money for an instrumentation amplifier than you do for an op amp. Okay, So input offset voltage is a fairly simple concept, and we're mainly concerned about it when we're trying to figure out what is the range we can have on Vout. What does that translate to as the range we can have on the inputs? Because we have to take the input offset voltage into account there also. All right, what about bias? I talked about input offset voltage so far, but there's two other concepts we get. Input bias current and input offset current. Okay, so the first concept was for voltage. Now we're going to look at current. We said that op amps take no current. Well, of course, that's a lie. They're real-world parts. They do take some current. How much current do they take? Well, that's what the input bias current is talking about. Again, we have two inputs there, positive one and a negative one. And so we may have some current going in or current coming out of either of these two things. And generally the bias current is you take the positive and the negative inputs and just sort of average their two currents. That's the input bias current. The input offset current is generally the difference between the two currents. So the average or the difference are the bias or the offset. And ideally, these are all zero. In practice, of course, they're not. For instrumentation amplifiers, you're generally going to have the bias current being less than 20 nanoamps. And you'll have the offset current generally being less than the bias current. Not always. You have to be careful to read your specs. I have seen some amplifiers where they had very, very low bias currents, but then they had huge offset currents, which sort of defeats the purpose. And for an op amp, again, they're usually not as good, less than, say, 250 nanoamps. Now that's, again, 90% of the parts have ones that are within these specs. There are ones that are much better and ones that are much worse. One interesting phenomenon is that there's a bit of a trade-off in the design of the circuits between getting a good input offset voltage and getting a good input bias current. And it depends on what sort of transistors you use at the front end of your amplifier. You can get ones that take very low currents. In fact, the very cheap ones that we use in the class, the MCP 6004 chips, take only typically a picoamp of input bias current, so quite good. But their offset voltage is like 4.5 millivolts, which is pretty crummy. And that's because they're using probably MOSFET transistors in the input stage, which are very low current, but a little difficult to match. Other circuits may have a very well-matched pair of transistors, but because they're not MOSFETs, they end up having a much higher current need. And so, trade-offs in design. You have to decide when you're picking an amplifier, which of these properties do you really care about? Because it's hard to get both a very low input offset voltage and a very low input bias current. For some circuits, one of them is much more important than the other, and so you need to pick the parts you need appropriately for the particular application. It isn't universally this op amp is always better than that one, or this instrumentation amp is always better than that one. Nearly always there's a trade-off, and picking the ideal trade-off given the parts available is often quite tricky. For what we'll be doing in this class, because we're using an op amp that has extremely low bias current, we're not going to think about the bias current and the offset current really at all. It, however, has a big offset voltage. And so that we will be concerned with, because when we design high gain amplifiers, if you haven't taken the offset into account, you'll get clipping. You'll take that offset voltage and amplify it up until you hit one of the power rails, and that's not going to be good for your system. So be aware of input offset voltage, and when appropriate, like when figuring out the gain you need for an amplifier, think about what effect would having the input be a little bit off from zero due to this circuit.